In this video, we finally get to the purpose of all this series business. We start talking about Taylor and Maclaurin series. And in fact, we'll focus mostly on Maclaurin series today. But we're going to develop all of this through the lens of the Taylor series. And so the Taylor series is a specific series depending on the type of function you have. And the Maclaurin series is a specific case of a Taylor series. Maclaurin series is typically easier to find. It's just one small thing different. And hopefully I'll outline that. So let's get started. Basically, we start with a regular power series. We say I have a function that's written as a power series, a sub n x minus c. So I have a center at c, all to the power n. And when I expand, that looks like, this second line here, a sub 0 plus a sub 1 x minus c to the first plus a sub 2, so on and so forth. And really what we're going to be looking for is if we can find a way to regularly, distinguish and determine what these a values are. Because so far, they're either just been really general, or I've given you a formula. When we were looking at radius and interval of convergence, we just had, hey, here's a series, tell me where it converges. Okay? And those a sub n's were already given to you, and it wasn't at all discussed how they were found. So basically what I want to know is there a formula? Is there a formula for a sub n? And if so, how do I find it? Well, what we're going to try to do is use this expanded form here to determine what these a values are. And we're going to use what we know about calculus to help us with that. And what we notice is that if we evaluate that function f of x at the center, if I take f of x and I plug in c, by setting x equal to c. And what we notice is that all of those x minus c's, when x is equal to c, are going to disappear. So everything there in orange in the second line is going to go away, and I'm going to be left with just a sub 0. So when I do that, I get f of c is equal to a sub 0, and if I just kind of rearrange that, I find what a0 is. I've got that first a value. And what we're going to hopefully develop here is a formula for then the rest of the a values. It's going to take a minute, so bear with me. But we're going to go through and then find a couple more so that we can develop that pattern. What about, say, a sub 1? Well, I can't just plug in a number to f of x here and keep everything, and get rid of everything except for a sub 1. But the thing I know that will do that will eliminate the constant out front and then leave the next term with that x, with the linear x minus c there, is if I take a derivative. So what we do is we take f prime of x, and when we do that, we're taking a derivative of a polynomial, right? So the power of every one of those x minus c's is going to decrease by 1. And for the first one there, I'm taking the derivative of a sub 1 times a linear function times x minus c, and the derivative of that is just the constant, right? It's just a 1. First term, derivative of a0 is 0 plus a1, and then everything is going to have a power down in front and a decreased power. So it should see 2a2 times x minus c to the first, plus 3a3 x minus c squared, 4a4 x minus c to the third, and so on. Okay, now if I plug in x equals c, I will get rid of everything except for a1. And that's because there's an x minus c with every other term in the derivative. Okay, so plugging in c leaves me with a1, and if I just rearrange that again, I get a1 is equal to f prime of c. Okay? So far, there's not much of a pattern. a0 is f of c, a1 is f prime of c, maybe a2 has to do with f double prime. You would be correct in thinking that. Given my derivative here, let's speed that up. Given my derivative, I take a second derivative to find a2. Same kind of idea. And again, the powers are going to decrease by 1, and that same constant, or the same exponent, is going to come down in front. And again, I'm going to evaluate at c. But this time, there's going to be an a2 left over. But the interesting thing is now there's a constant that comes with a2. I get 2a2. And when I rearrange to solve for a2, I have to divide by 2. I get f double prime of c divided by 2. So now what I was thinking about my formula is a little broken, because I was thinking it was just the derivatives, but now I know that there's a constant, or there's going to start to be extra numbers in there that I got to pay attention to. Let's do another derivative or two and see what happens, and see if I can start to develop an idea. And what I want you to pay attention to is kind of these terms here. Let's see if I can write these terms here and see how those change and grow as I take derivatives. All right. So the idea is with a3, when I take another derivative, a third derivative, and there I'm looking at the second derivative to do that, I take a look at the second derivative, and when I take another derivative, the first term I see is actually this third term here. I get 3 times 2, a3 by itself. And then the term with a4 is 4 times 3, and I bring the 2 down. 4 times 3 times 2. a4 times x minus c to the first. And then the next term is going to have 5 times 4 times 3 times a5. And we notice something about these guys, like I told you, pay attention to. Again, I'm going to plug in c, the center. For the first term there, I get 3 times 2 times a3, and every other term here is going to disappear, right? Because there's an x minus c in every one of those terms, in every one of those terms. So those all disappear, and I'm left with just a3. But with a3 here, I see 3 times 2 is 6. I'm actually not going to write that as 6 because I want to see it written as 3 times 2. It's going to help me visualize the pattern. But I solve for a3 to be f triple prime, the third derivative, divided by 3 times 2. And we're starting to see this, shape, 3 times 2, 4 times 3 times 2, 5 times 4 times 3, you might guess, times 2, so on and so forth. Those are starting to look like factorials. If I just kind of quickly go and find a4, we expect a4 would probably be the fourth derivative at c, and that's a notation there. Instead of 4 primes, I'm going to write the derivative there in parentheses. That just means fourth derivative, divided by 4 times 3 times 2. So we can come up with a general formula, an. I could keep going, but eventually what we begin to see is this pattern. So an is a formula for all of these a's, right? And it's a way for me to collect them all and write them as just one general form. What I see is a derivative. In fact, the derivative matches the term that I'm at, right? So here, a4 has a fourth derivative. a3 has a third derivative. So the n matches the derivative that I'm at. So that's f to the power in parentheses. It's not really a power, it's just the nth derivative. And it's evaluated at c divided by, and in the bottom we have the factorial that corresponds with n, with the index that we're at. So 4 factorial is 4 times 3 times 2. 3, the a3 has 3 times 2 times 1. We just don't write this extra 1 down here, though it's there. So in the bottom, I have n factorial. Okay? Now I have a formula for these a sub n's. That's a way to calculate the coefficients of my power series no matter what function I have, as long as the function I can take derivatives of it and plug in c. Okay, so what we've got, so our general power series, f of x is equal to this guy here, a sub n x minus c to the n. I can write substituting in what I found for a sub n. So what that is really f of c plus f prime of c times x minus c plus f double prime of c divided by 2 factorial x minus c squared plus f triple prime of c divided by 3 factorial x minus c to the third, so on and so forth. Okay? We're going to use both of these notations, right? Where I write it as the summation, and where I write it in the expanded form where I see those individual terms. I'm going to do both things. The condensed form is nice, right? I don't want to have to write out every single term every time I write a function like this. I want to be able to write it in summation notation. So what we're able to do is find a power series for any function as long as it's differentiable. This power series, what we call is a representation for f of x. It's a representation for the function we have. It's called a Taylor series. The Taylor series, or TS, for f of x at x equals c. Okay, that's what it means to be a Taylor series. So this is what it means to have a Taylor series. We're able to write the function. We're able to find those coefficients, those a sub n's for the given function we have. So what I want to look at now is a specific case of this. It's what we call the Maclaurin series. When c is 0, the Taylor series, it's still a Taylor series, but it's called a Maclaurin series. Okay? And what we see is that the center c is just 0. So that x minus c is just going to be written as x, right? Because x minus 0 is just x. That's what our formula will be for a Maclaurin series. And that's what we're going to focus on in this video. I'll find a couple different Maclaurin series and show you that process and maybe some of why it's useful. This implies, of course, that we can find or we can write any differentiable, that's the key, it's got to be differentiable function as a power series. Okay? And that's an awesome thing. And it's especially nice, as I alluded to in the last video, for transcendental functions, right? E to the x, sine, cosine, tangent, those trig functions, natural log, functions that don't already have a representation as just x squared plus 4, that kind of thing. We're able to write them kind of as such. And there's a nice kind of technique for finding a Taylor series or a Maclaurin series for a specific function, for a function f of x. And what we'll do is I'll outline that in an example here. I want to find the Maclaurin series for f of x equals sine of x. Okay? And I'm, of course, going to use kind of the formula to do that. We saw from the last bit there that the formula for Maclaurin, and Maclaurin means that I'm going to use a center of 0. So my function is then going to be the sum of all the derivatives evaluated at 0 divided by n factorial and then multiplied by x to the n. Well, what is that? What is that summation? I'm going to go out some terms. That's the original function. When n is 0, I have the original function, the 0th derivative, no derivatives, the original function evaluated at the center, plus the summation says I take the next when n is 1, which is the first derivative evaluated at 0 times x to the first. When n is 2, I add the second derivative evaluated at 0 divided by 2 factorial x squared. When n is 3, third derivative divided by 3 factorial x cubed, so on and so forth. So my mission is really to find what are these derivatives evaluated at 0. And then I will collect them and write them as a summation. I'll write them as a formula. Okay? So the process I go through for this is when n is 0, I take the 0th derivative of my function. What's my function? It's sine of x. And then I evaluate that at the center, 0. Sine of 0 is 0. So we got to know a little bit to be able to do this. Okay? When n is 1, I take the first derivative of sine of x, that's cosine of x, evaluated at 0, and that's 1. When n is 2, I take the second derivative, that's minus sine of x, evaluated at 0 is 0. Okay? When n is 3, I take the third derivative. Derivative of minus sine is a minus cosine. Evaluated at 0 is a negative 1. Keep going. When n is 4, I'm just going to keep doing these until I kind of come full circle. And here I found it. I'm back to sine of x with a fourth derivative. Derivative of minus cosine is positive sine. And when I evaluate that at 0, I get 0. So I'll cut it back to where I started. Let's just do one more for the sake of it. The fifth derivative. Derivative of sine again is cosine. And cosine evaluated at 0 is 1. Okay? So what I've got are these three guys really that are showing up. Because the derivative for the even ends, right? N is 0, 2, and 4. The coefficients are 0. Right? I see zeros for each of those. And I'll show you where those end up. But really what I've boxed in pink there is what's going to show up in my series. So I'm going to rewrite this summation line, but I'm actually going to plug in what these coefficients are. So here I have f of 0 is 0. That's when n is 0. That's right there. So my function I write as f of 0 is 0 plus f prime of 0 is 1. That's this guy here is 1. X to the first plus f double prime of 0 is 0 divided by 2 factorial x squared. F triple prime of 0 is a minus 1. Minus 1. So that goes in the numerator. F triple prime of 0 when n is 3 divided by 3 factorial x cubed plus when n is 4, I get another 0 divided by 4 factorial x to the fourth. When n is 5, I get a 1, right? 1 shows up. If we were to keep going, I didn't find these derivatives, but I think we have a pretty good idea of what's going to happen. Every other term is 0. So since I got a 1 in the fifth term there, I'm going to get, or when n is 5, I'm going to get a 0 divided by 6 factorial times x to the 6th. And then every time I get a term that shows up, it's of opposite sign, right? So the 7th here should have a negative 1, and so on and so forth. Those odd terms are the only thing that shows up in my series, okay? So sine, and in fact we'll see cosine, is a little bit special when we find the Maclaurin series, specifically centered at 0, as we get half the terms basically disappear. It's either even or odd depending on what you're working with and what your center is. So we've got all the odd terms that are showing up here boxed in pink. So I want a way to write that. Basically, I'm going to write what shows up. I'm going to write those down again. So I have this first term is x plus negative 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th, so on and so forth. And now comes the more tricky part, if it hasn't been difficult yet. The tricky part here is to condense this and write it into summation notation. Okay? So basically what I want to try to do is write this as a sum from 0 to infinity. But what I'm going to do is basically start this at 0, and I want to be able to write it, even though the odd terms were the only ones that showed up, right? So up here I had n being 1, n being 3, and n being 5, so on and so forth. I want those to correspond to kind of new n's now. I want to start at 0. I want the next term to be when n is 1, the next when n is 2. And to do that, I have to be a little strategic here. I have to find a way to write these terms so that only the odd terms show up. Well, we know how to write odd terms. We write odd terms with like a 2n plus 1 or a 2n minus 1. So I'm going to use that as to my advantage. When n is 0, I should get an odd term. I should get 1. So in fact, what I think I want here is 2n plus 1. When n is 0, I get 1. When n is 1, 2 times 1 plus 1 is 3. When n is 2, I get 5. When n is 3, I get 7. So that's one of the ways that we kind of do this, and we collect the terms that we want. Since I only have odd terms here, I want my series to start at 0 and only have the odd terms show up. So the way I do that, what have I got going on? I've got an alternating sign, right? So every kind of odd term now is negative. So when n is 1, I've got a negative. When n is 3, I've got a negative. So what I want is an alternating piece. I want -1 to a power, and that power here will be n, right? Because when n is 0, I've got a positive term. When n is 2, I've got a positive term. So -1 to the n works just fine there. I've also got odd powers of x. So that's x to the 2n plus 1 power, and those are also all divided by odd factorials, right? Under the first term there, I've got like a 1 factorial, but 1 factorial is 1. We don't need to write it. They start showing up when n is 1, I get a 3 factorial. Well, when n is 1, to get a 3, I've got to use 2n plus 1, so I have 2n plus 1 factorial. And that should work for the rest of the series. Okay? So what we've shown here is that by the formula for Maclaurin series, I found these coefficients. I found the derivatives, the n derivatives evaluated at the center, and I've collected those in this nice little summation notation. So what we've got is that sine of x is exactly equal to that guy, that summation. I want to know, is this really equal, and for which x's? Does that series converge? For which x's does this Maclaurin series converge? And we can tell by using the ratio test. Basically, what I want to find here is the interval of convergence. For which x's does this series converge? For which x's can I write this series for sine of x? So I go through my ratio test. I'll go a little quickly, but kind of slow down in certain places. The n plus 1 term, I take every n in my series and replace it with an n plus 1. So the first time we see this weirdness happen is in this x to the power 2n plus 1. I'm replacing n with n plus 1. So I see 2 times n plus 1 plus 1. That's going to happen again in the denominator. 2n plus 1 factorial is 2 times n plus 1 plus 1 factorial. Times the reciprocal of the nth term. I just rewrite what's in my series there, but upside down. 2n plus 1 factorial divided by that guy there. In absolute value. And again, my ratio test says if this limit is less than 1, I have convergence. If it's larger than 1, I have divergence. So basically, what we're going to find is a group of x's for which this series converges. Hopefully. Maybe just the center, maybe all x's, maybe a specific interval. We'll see. This 2 times, this 2 times n plus 1 is really just 2n plus 3, right? If I distribute the 2n plus 2 plus 1 is 2n plus 3. And that also happens in the exponent. So that first expression there I write as minus 1 to the n plus 1, x to the 2n plus 3 divided by 2n plus 3 factorial. And I'm just going to leave that second term the same. And then I'm going to try to simplify. Okay, and the way I'm going to do this is like I did before with the ratio test. I want to pull different things off and apart and try to cancel and factor and this and that. And the first thing I see is this -1. I've got a -1 in the top and the bottom, but one of them has a higher power by 1. So I'm going to take out that numerator. I don't know why that piece happened there. Sorry about that. I'm going to factor out a negative. And I'm also going to mess with the factorials here. I see 2n plus 3 and a 2n plus 1 factorial. 2n plus 3 factorial is greater than 2n plus 1 factorial by two terms, and those two terms are 2n plus 3 times 2n plus 2. If I pull off those two terms, what's left is 2n plus 1 factorial. Now to the negatives, I have a negative 1 to the n plus 1, which I will write as negative 1 times negative 1 to the nth. And a similar thing with x to the 2n plus 3. I see that that's going to cancel with x to the 2n plus 1, but there's going to be an x squared that I can take apart. If I take off an x squared, remember when I multiply like bases, I add the powers. So 2n plus 3 is the same as 2n plus 1 plus 2, right? And on the right, I leave everything the same, and I start to cancel. So the minus 1 to the n's are going to go away. Minus 1 to the n's. The x to the 2n plus 1's are going away. The factorials there are disappearing. And what I have left are those two terms in the denominator, 2n plus 3 and a 2n plus 2. And I have a negative x squared up top. Thankfully, I have absolute values. That negative is just going to disappear. And I'm left with a limit as n goes to infinity of x squared over those two terms of n. And as n gets bigger, doesn't matter what x squared in the top is doing. X squared has nothing to do with n going to infinity. Denominator's growing. And that limit there should be 0, which is less than 1. Since that limit is less than 1, for any x, we say the series converges for all x. Okay? And what that means is that we can write this sine of x equal to the series. This series converges for all x. We can write it as sine of x for all x. So we can always write sine of x as that Maclaurin series. Always. That converges for no matter which x I plug in. Okay, and that's a powerful thing. That's that third case of that theorem 9.20 that we talked about. The third case is that we converge everywhere. Okay, and that's really what I said then, is that's the situation that we want to be in. And here's why. It's because I can write then the function that I'm working with as the series no matter what x is. I can plug in any x to that series and get exactly what I would get for sine of x, sine of that value. Awesome. Super cool. Super cool. So there's the process for which we find the Taylor or Maclaurin series, right? My center was 0. And I just wanted to show you here, we don't necessarily have to do this every time, but it is important to know where those series converge or diverge, right? For what's the interval or radius of convergence. And I want to do another example where I find the Maclaurin series. I'll go through it a little quicker because we're going to go through that same process where we find the derivatives. This example here is with e to the x. And again, I'm looking at Maclaurin series. So my center is 0. I'm going to write that formula down again. Function is given by the summation of the n derivatives there, evaluated at 0, divided by n factorial times x to the n. Cool. So what I really need to do is find the 0th derivative at 0, the first derivative at 0, the second derivative at 0, so on and so forth. And actually that third one there has a c that should be a 0. I'm sorry about that. Okay, so for each of these n's, I'm going to go through kind of the same process and find some derivatives of my function. When n is 0, I'm at the original function, that's e to the x. Evaluated at 0, that's 1. E to the 0 is 1. When n is 1, I find the first derivative. Derivative of e to the x, e to the x. Evaluated at 0, 1. Uh-oh. Guess what's going to happen? For every derivative here, because of the way that e to the x behaves, each derivative is going to be e to the x, and all of those evaluated at 0 are going to be 1. I'll just go through these next three. Lightning speed, third derivative, evaluated at 0 is 1. Fourth derivative, evaluated at 0 is 1. Fifth derivative, evaluated at 0 is also 1. It's an easy one. Easy, easy. Okay. So now I challenge you to write out the terms that show up. All right, this is a bit different than sine of x, where I had terms that went away. Some of these coefficients were 0. That doesn't happen here. All of the coefficients are 1. And that's kind of a nice thing. I replace the series expansion there above, where I'm actually going to plug in these values. My function f of x is 1 plus 1 times x to the first plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the fourth, so on and so forth. These all give me my series expansion for the specific n below there. And what I want to do is, again, collect this all in summation notation. I want to figure out a way to write this as a sum. And e to the x, then, every coefficient is 1. So whereas before I had some alternating piece, I had some -1 to the n, that doesn't show up here because there's no alternating sign. I don't have every odd term or every even term, so I don't need a 2n or a 2n plus 1. All I've got are powers of x and the factorials in the denominator. And everything matches with the term with the specific n. When n is 0, I need a 1 to show up. Okay? So what I've got is n factorial. Remember, 0 factorial is 1. Yeah? When n is 1, I need a 1 factorial in the denominator. 1 factorial is 1. Perfect. When n is 2, I need a 2 factorial. Perfect. So that n factorial is going to work perfectly there. In the numerator, I just have powers of x. The first term has no powers of x, x to the 0. The first term, I guess, when n is 1, has a first power of x, x to the first. When n is 2, I have 2 powers of x. The power matches the term. So x to the n will do it fine for me. And we've shown in the previous video that this series converges. This is another case 3, converges for all x. We applied the ratio test, which means that we can write the function e to the x as that series for all x. And that's awesome. That's awesome. This is another case where we can write the series and the function. We can interchange them. It doesn't matter. And there are situations where we would prefer the power series or the series representation as opposed to the function. And I'm not going to get too much into that. Mainly, just how to find these Taylor series, Maclaurin series. In the future, most of the time, you'll either have used these enough where you just know them, or you'll look them up. You don't necessarily have to go through this process every single time. Of course, on the final, I'll ask you to go through the process, right? I'll ask you to go through and figure out what this pattern is, how I find it, by taking these derivatives, and then to write it in summation notation. So far, we've only dealt with a center at 0. Okay, in the next video, I'll do an example where I change the center. Things change. I'll let C be something different. I'll basically just now find a Taylor series instead of the specific Maclaurin series. What I want to do here is use an example with this e to the x, and I want to find a Maclaurin series for e to the x squared. Now here, because I know the series for e to the x, given the series for e to the x is this guy here, I don't have to go through and then take all the derivatives of e to the x squared. This is an awesome side effect of knowing the Maclaurin series for some specific function and then using it to find a series for some related function. Okay, and I'll do another example on the next slide here too. But with this e to the x squared, if e to the x squared is g, I'm going to call e to the x here f of x. So that means that g of x is really just taking f, but plugging in x squared. Instead of in the exponent just x, I have an x squared. So that's taking my function, the one that I know the Maclaurin series of, and plugging in x squared, which is sweet. Because when I go out terms here, I'm able to find e to the x squared is 1 plus, instead of x, I have x squared. Instead of x squared, I'm going to have x squared squared. For every x here, I'm going to plug in x squared, so on and so forth. In summation notation is really the way I want to write this, right? The shorthand version. I have a representation now for g of x, or e to the x squared, as the sum of, instead of x to the n, it should be, each of these terms is going to have x squared to the n, right? I'm going to see something like an x to the x squared here, and x to the fourth here, x to the sixth here, all even powers of x. And the way that we'll be able to write that, I'll show you in just a second. I still have the factorials. The way we write those evens is with x to the 2n. X to the 2n, right? For every n, the 2n there is going to represent an even. So when n is 0, I've got x to the 0, which is 1. I see that here. When n is 1, I've got x to the 2 times 1, x squared, that's there. When n is 2, I've got x to the 4th. When n is 3, I've got x to the 6th, so on and so forth. There's my series for e to the x squared. And all I had to know was the series for e to the x, and I could use that to my advantage. One more quick example. I want to find the series for e to the x over x. So a very similar example, but this time I'm dividing by an x instead of having a different exponent. This series here, I take the series for e to the x, 1 plus x squared over 2 factorial, x squared over 3 factorial, so on and so forth. Each one of those terms is just going to be divided by x. That's it. That's it. All I've got to do is take each of those terms and divide it by x. Let's just rewrite this a little bit. And what I've got here is 1 over x plus 1, right? X over x is 1. When I divide x squared by x, I just get an x. All of these powers are decreased by 1. So before, when n was 0 here, I had a 1, but now I have a 1 over x, right? So the power of x is 1 less than what it was before. The factorials still match up perfectly, but when I go to write the series here, what I've got to do is take the original series and divide it all by x. And the effect that has, again, is that the powers are all 1 less. So instead of x to the n, what I should see is x to the n minus 1. And that series is going to represent this e to the x over x. All using what I know about the Maclaurin series for e to the x, just dividing by x. I could also do a series for, say, like x e to the x, right? Then every power would increase by 1. I can do all sorts of different things. But there's just an example or two where we can use the series that we know to find other related Maclaurin series. Like I said, in the next video, I'll do an example of an actual Taylor series. Not that it's different, really, but just the center is not 0, necessarily. So a Maclaurin series is a Taylor series with a center at 0. Other than that, that's all I want to show you here. After Taylor series, at a specific center, I'll talk about Taylor and Maclaurin polynomials, and then we will be done. Thanks for watching.